Welcome to the Mechanics of Solids lecture series. In this series of videos, we're looking at examples of plane stress and stress transformations. Our learning objectives are to compute the stresses at a point due to common loading and represent the stress state as plane stress. Second, given a plane stress state, we're asked to compute the stress state with respect to an arbitrary rotation theta of the planar axes. And the stress transformation equations that we'll use are summarized here. Our first example is a problem from Mechanics of Materials by Timothy Philpott, Wiley 3rd edition. We're asked to evaluate the plane stress state at K and sketch the stresses on a picture of the element. And looking at the shaft, the point K is right there. We're given applied torque TB and TC and an axial force P at the end with the loads as given, and the diameter of the solid shafts as given. And what we need to find for this problem, the plane stress state, so that means we need to find the values of sigma x, sigma y, and tau xy at point K, and our working units will be megapascals. I'm going to start by drawing a little picture of the shaft, a segmented shaft. Okay, and adding the loads, we have a torque TB, and if we wrap our hand around the torque in the direction, we can see that it's a double arrow pointing to the right. TC at the end, acting in the opposite direction, and an axial force P also acting inward. And point K is right here in the middle of the shaft. So I'm going to make a cut at that location, draw a free body diagram to the right of the cut, put my loads back on, TC and P at the end, and at the location of the cut, my internal forces, I would have an F equal to P, and I would have an internal torque T equal to TC in the direction shown. So those internal forces are going to determine the stresses at that location. We know that the internal force F gives rise to an axial stress, sigma x, equal to F over A. We know that the internal torque T gives rise to a shear stress, tau xy, that is equal to TR over J. And there's no loading that's going to cause a stress sigma y in the y direction, so we'll conclude that sigma y is equal to 0. Okay, so we need to do some calculations. To calculate sigma x, we need to calculate the cross-sectional area of shaft 2. A would be equal to pi over 2 times pi over 4 times d2 squared. It's equal to pi over 4 times 25 millimeters squared, or 490.9 millimeters squared. Then sigma x is equal to F over A. F is equal to P at 22 kilonewtons, or 22,000 newtons. And we know that this stress is going to be negative because the force is acting inward. It's compressive. Divide by the area, 490.9 millimeters squared. And this stress is negative 44.8 megapascals. And that is sigma x. Okay? Tau xy equals TR over J. We need to compute J. J for a solid circular shaft is pi over 32 times d2 to the 4th equals pi over 32 times 25 millimeters to the 4th, which is 38,350 millimeters to the 4th. So we'll compute tau. Tau xy equals T, 175 newton meters. I'm going to change that to 175,000 newton millimeters. This is a good review of torque. Times R, the radius of the shaft would be 25 over 2 millimeters, divided by J, equal to 38,350 millimeters to the 4th. This gives a value of 57.04 megapascals, equal to tau xy. And what about the sign? Okay, if we visualize the torque it's going to cause, this torque in the direction is going to cause twisting like this. Okay, it's going to cause the shaft to twist about itself in that direction. And so the torque would be positive, or sorry, the shear stress would be positive by inspection. Okay, so now the last step of the problem is to represent these stresses on a little sketch of the element of point K. So I'll draw my little sketch like this, just a little block. Sigma x is negative, so I draw arrows pointing inward, 44.8. Okay, sigma y is equal to 0. Tau xy equal to 57 positive, so I draw the arrows in the positive direction on the positive face, negative direction on the negative face. 57.04. Okay, and that's it. Just let me clarify, units are megapascals. And that concludes this example.